Today we are going to discuss the conservation of angular momentum. It says that if the external torque acting on the system is 0, the net angular momentum remains conserved. That is, we can say if tau net, that is the external torque, is equal to 0, it will imply L will be equal to constant. Now let us explain this point. As we have already studied, external torque acting on the system is equal to rate of change in angular momentum. So we can say tau is equal to dl upon dt. Now, if tau is equal to 0, this implies dl upon dt will be equal to 0, which will give L is equal to constant. Since we know that differentiation of constant is 0, thus angular momentum will be constant. Now let us see the condition for the torque to be 0. As we have already studied, torque is equal to Rf sin theta. Thus torque will be 0 if R is equal to 0, which means that the force passes through the axis of rotation. Secondly, we can say torque will be equal to 0 if force is equal to 0 or negligibly small. Finally, torque is equal to 0 if sin theta is equal to 0. That is, if theta is equal to either 0 degree or 180 degree, which means that the force is either parallel to the radius vector or it is anti-parallel to the radius vector. For example, we can say since centripetal force is acting along the radius vector, so it will not impart any torque on the particle. We can cite numerous applications of the conservation of angular momentum in practical situations also. For example, that as the spring jumper glides in air from the spring, he folds his body in order to make more circular turns in air. And as he approaches nearer to water, he opens his body so that his angular momentum decreases, so that his velocity decreases due to increase in its moment of inertia. During spinning, a dancer takes his or her leg inward. In both the cases, as we know that L is equal to I omega, so folding the body or taking the leg inward decreases I. Since L is constant, I will be inversely proportional to omega. I decreases, this implies omega will increase.